Hey everyone, welcome back to the deep dive. We all want to understand things thoroughly, but sometimes it feels like there's just so much information out there.
Right, and it can be overwhelming to even know where to start sometimes.
Totally. It's like our brains can only process so much at once.
Exactly, and that's precisely where cognitive load theory comes in.
You got it. This theory helps us understand how we learn complex things.
It was first outlined by a researcher named Sweller, way back in 1988.
Yeah, 1988.
But here's the thing, it's still hugely relevant today.
Absolutely. It's like a cornerstone of learning research, and that's actually what we're diving into today.
So this isn't just some old theory gathering dust. The field is constantly evolving.
Oh, for sure. Always new research coming out, giving us even better ways to understand learning.
Exactly. And today we're focusing on some key advancements from the Third International Cognitive Load Theory Conference.
From 2009?
Yeah, 2009. The goal here is to make this research practical for you.
Right. Like, how can you use it to learn more effectively right now?
Yeah, and also understand why some teaching methods work better than others.
Makes sense. So, we've combed through tons of research, and we found three areas with really exciting developments.
Sounds good.
First up, we'll explore something called worked examples.
Ooh, interesting.
It's basically learning by studying step-by-step solutions. Then we'll look at animations and videos
Ah, yeah.
and see how their fleeting nature, that whole transience thing can affect what we actually learn.
Right, right.
And last but not least, we'll check out how scientists are measuring what's happening in our brains during learning.
Fascinating stuff.
It is, right. So if you've ever struggled to learn a new skill or felt like there must be a better way, this one's for you.
Yeah, we're all about giving you actionable strategies based on, how your brain really works.
All right, so let's start with worked examples. It's a technique that's proven to be really effective.
Really?
Yeah, especially when you're starting out with something totally new. Imagine you're trying to solve a tough math problem.
Okay, I'm imagining it.
A worked example doesn't just give you the answer, it shows you each step to get there.
Oh, I see.
It's like having that instruction manual laid out in front of you.
Makes sense.
Now, the research on this is pretty solid,
Hmm.
going all the way back to Cooper and Sweller's work in the 80s,
Oh, yeah?
and continued by researchers like Payas in the 90s and even Van Gogh more recently.
I see.
They all found that for beginners, studying these step-by-step solutions leads to better learning,
Wow.
and it helps you apply that knowledge to new, similar problems.
Interesting.
But what's really interesting is that it can be faster and easier than figuring it out yourself from scratch.
That's kind of counterintuitive.
Yeah, right. You'd think that struggling through a problem would make you learn more.
You would think, yeah.
But when you're a novice, just figuring out where to start can overload your brain.
Ah, makes sense.
So seeing how an expert approaches it frees up your mental space to focus on the underlying principles.
Interesting, like learning the basics before trying to compose a whole symphony.
Exactly. And this phenomenon is called the worked example effect.
Okay, so worked examples, they really work.
Yeah. But there's another question that comes up, especially with online learning and intelligent tutoring systems.
Oh, right, those systems that adapt to you as you learn.
Exactly. And this is what researchers Codinger and 11 called the assistance dilemma back in 2007.
What is that exactly?
It's basically about how much help learners really need.
Oh, right, like should you let them struggle a bit or give them more guidance up front?
Precisely. And a study by Salden and his colleagues in 2010 gives us some insight here.
Okay, what did they find?
They looked at situations where learners could get help on demand while they were working on problems.
Like having a tutor right there with them.
Exactly. Then they compared that to just learning from worked examples.
Fascinating. So which one worked better?
Well, what they found was that even with that on-demand support, worked examples were often more beneficial. So sometimes seeing a well-structured solution from the start is better than constantly needing help when you get stuck.
That's really interesting.
And this highlights how good examples can reduce what we call extraneous cognitive load.
Extraneous cognitive load.
Yeah, it's that mental effort that doesn't really contribute to learning.
Ah, I get it. So it's like mental clutter.
Exactly. So worked examples are great when you're new to something.
Definitely.
But how can we make those examples even better?
Good question.
And that's where the research by Whitwer and Renkel comes in.
What did they do?
They reviewed tons of studies on the effect of adding explanations to worked examples.
Okay, so like providing more context or reasoning behind the steps.
Exactly. And what they found is that explanations do have a small positive effect.
That makes sense.
And they seem particularly helpful for understanding the why behind things, not just the how.
Right, that deeper level of understanding.
But here's the catch. Just reading someone else's explanation wasn't always better than trying to explain it to yourself.
Hmm, interesting. So the act of explaining it yourself might be key.
Yeah, that internal processing seems to really solidify learning. So passively reading a work example isn't enough.
You need to engage with it. Really try to understand each step.
Right. Even articulate it in your own words.
Yeah, that makes sense. It's like teaching it to someone else.
Exactly. So that's something to keep in mind when you're using worked examples.
Okay, I'll keep that in mind.
Take your time, understand each step, and try to explain it to yourself.
Got it. Self-explanation is key.
Awesome. So worked examples are great for, static information. But what about dynamic stuff like videos and animations?
Yeah, that's a good point. We see those everywhere in online learning now.
Right. Let's dive into that.
Okay, so Wooters and his colleagues, they pointed out in 2008 that animations and videos are becoming super common in education.
Makes sense. They can really help visualize things.
Yeah, like complex processes, right?
Absolutely. But they also bring a unique challenge. Transience.
Transients.
Yeah. Sounds fancy, but what does it really mean for learning?
Okay, think about it. In a video or animation, information pops up and then vanishes.
Right. It's fleeting.
Exactly. And as Ayers and Paz discussed in 2007, this can overload your working memory.
Like trying to hold on to too many things at once.
Exactly. You're processing new information while trying to remember what you just saw.
Oh, I see.
Important details can slip away or not really sink in. It's like trying to solve a puzzle where the pieces keep disappearing.
Yeah, that sounds frustrating.
It can be, but there's a cool exception to this.
Oh, what's that?
Animations showing human movement.
Really?
Yeah. Huffler and Leutner in 2007 and Van Gogh and his team in 2009, they found that our brains might process those differently.
Interesting. How so?
Well, it's thought that our mirror neuron system might be involved.
The system that helps us understand and imitate actions.
That's it. So it could help us process those animations more easily.
So if you're learning a physical skill like an exercise or a surgical procedure, watching an animation of it might be super helpful.
That's the thinking.
Yeah.
But for other animations, like how a car engine works or a biological process,
Yeah.
we need strategies to deal with that transience problem.
Makes sense. So what are some ways to make learning from animations less overwhelming?
Well, one key strategy is cueing.
Cueing.
Yeah. It's about guiding your attention to the important parts of the animation at the right time.
Oh, okay.
De Koning and his colleagues described this in 2009. It could involve visual cues like arrows or highlighting,
Right.
or even narration telling you what to focus on.
Like having a tour guide pointing out the key detail.
Exactly. So when you're watching those instructional videos, pay attention to those cues.
They're really there to help you learn. Okay, what else? What other techniques are there?
Another good one is segmentation.
Segmentation.
Yeah, Mayer talked about this back in 2005. It's simply breaking a long animation or video into smaller chunks.
Oh, right, like chapters in a book.
Exactly. Instead of one long stream of information, you have these natural breaks.
Okay.
And Spangers and his team, they dug into why segmentation works so well in 2010.
What did they find?
Well, most research on this includes pauses between those segments.
Makes sense.
So the question is the benefit just from those pauses giving you time to process?
Oh, interesting.
Or is it also because the breaks signal the end of one idea and the start of another?
Right, helping your brain organize everything.
Exactly. It's not just slowing down. It could be about how our brains naturally chunk information.
That's a subtle but important point.
It is. And they connect this to event segmentation theory, which suggests our brains break continuous experiences into events. So those pauses and animations might align with how our minds work.
Makes sense.
They also talk about the time-based resource sharing model of working memory.
Wow, that's a mouthful.
It is. But it basically offers another explanation for how those pauses free up cognitive resources.
So you can better absorb each segment.
Right. So if you're watching a long tutorial, look for those segments or even create mental pauses yourself.
Okay, that's a good tip. So segmentation helps the transience effect, but the reasons behind it are still being studied.
Yeah, it really shows how complex our brains are.
Absolutely. And understanding those mechanisms can help us design better learning experiences.
Exactly. We need to think about how our cognitive system handles different types of information.
Okay, so we've talked about learning from examples and managing information in animations. Now let's look at how researchers actually measure what's happening in our brains while we learn.
Ah, the really cool stuff.
Right.
Traditionally, we've used what we call offline measures of cognitive load.
Like asking learners how much effort they felt they used after a lesson.
That's one way, yeah. It gives us some clues, but it's only an indirect view.
And it's after the fact, not during the learning itself.
Exactly. You might remember feeling overwhelmed, but not exactly when or why.
Right. And this is where online process measures come in.
As described by Van Gogh and his team in 2009.
Yeah, 2009. These methods capture cognitive load as it's happening.
In real time.
Right. And one of the most exciting developments here is EEG.
Electroencephalography.
Yep. Antonenko and colleagues highlighted its potential in 2010.
It's a non-invasive technique that measures your brain's electrical activity.
Using sensors on your scalp.
Right. And it gives us a continuous objective measure of cognitive load in real time.
So instead of just asking someone how hard they were thinking, you can actually see it happening in their brain.
Pretty cool, huh?
It is.
And Antonenko and Niederhauser, they provided a great example in 2010. They used EEG to study how we process hyperlinks online.
Oh, interesting.
Specifically, they looked at whether having a preview of the content behind a link affected cognitive load.
Compared to just a plain link.
Exactly.
What did they find?
Well, they were able to detect subtle differences in cognitive load right at the moment people were deciding whether to click.
Wow.
And it depended on whether they had that content preview.
That's really amazing.
It shows how EEG can zoom in on specific cognitive processes during learning.
Right, and how even small design choices can affect how easily we process information.
Exactly.
That's a game changer for understanding how to design better learning materials.
It really is. It goes beyond just looking at the outcome. We can actually see the cognitive processes happening.
That's incredible. Well, this has been a really insightful deep dive into the world of cognitive load theory.
It has.
We talked about how effective worked examples are, especially when you're starting out with a new topic.
Right.
And we tackled those challenges with the fleeting information in animations.
Like transients.
Exactly. And we discussed strategies like cueing and segmentation to manage cognitive load.
Practical tips you can use right away.
And finally, we explored the exciting potential of EEG for understanding what happens in our brains while we learn.
Yeah, real-time insights into cognitive processes.
It's clear that cognitive load theory is a field that's constantly evolving and giving us valuable insights into how we learn best.
And how we can design better learning experiences.
Absolutely. So as a final thought, think about how these principles of managing cognitive load apply to your own learning.
Yeah, like how can you reduce distractions and optimize your mental effort to really understand things?
Exactly. How can you be more strategic about your learning and make it more efficient?
Think about using those worked examples when you're tackling new problems.
And be mindful of that transience effect when you're watching videos or animations. Look for those cues and segments.
It's all about understanding how your brain works best.
Exactly. Thanks for joining us for this deep dive into cognitive load theory.
We hope you found it helpful.
We'll see you next time.
Take care.
Bye.
Bye-bye.